Hi, I want to talk about coroutines in LLVM in the context of some work that I did in Swift. So coroutines were added initially in LLVM a couple years ago by Gornishinov. Slides. These were added a couple years ago by Gornishinov in order to support a C++ language feature, a prospective one. That's still not quite in the standard. We needed a very similar sort of feature for Swift that in pursuit of our ABI, and so I started looking at this, and I needed something a little bit different from what was already there in LLVM, and so that leads me to this talk. So what are coroutines is where I want to start. Coroutines are a very general language mechanism that's used to implement a lot of different language features, a whole family of different language features, from SyncAwait features like you see in C# to generators as you see in Python and a lot of other languages. I'm going to work through a very simple C generator feature in order to get the idea across. The idea here is we've got a generator function. This is like a normal function, except it can yield multiple times. It's going to take a C string that has some interior spaces. It's going to break it up into a bunch of separate C strings and yield each of those back to the caller. So here's the sort of general contract for that. And here's a sort of bit of code. You can see instead of having any returns in here, we've just got yields. These yields can yield something of the expected yield type. We've got a loop that's going over this. One of the really neat things that you can do with a generator that you can't necessarily do as cleanly or as encapsulatedly with an ordinary function is that you've got this encapsulated function, and therefore you can do all sorts of like state manipulation that would probably be too much to expect one of your callers to do themselves. So for example, this needs to return a C string. C strings have to be null terminated in order to be correct. So that we need to write that null terminator into the string. This is the string that we were passed in. Doing that modifies the original string. We don't necessarily want that. One of the nice things about being in a coroutine is that after we've yielded, we actually come back and we have an opportunity to clean up after ourselves. So we can just write the original space character that we found while we were traversing the string back into it. So that was the definition of a coroutine. Here's a simple little program that uses it. It's being called right here, and we sort of modified the for syntax to iterate over it. What does this look like at an implementation level? Well, we've got a call stack. We've got main, it's calling tokenize. Tokenize is calling the coroutine. The coroutine needs to yield back. It needs to give control back to tokenize. So here we go back to it. What do we do back in tokenize? Well, we call another function while we've been yielded back to. So this is tricky because if you're used to an ordinary call stack, this doesn't really quite work. We're calling back, we've already got something in that position on the call stack, so it's not really a stack anymore. And this is one of the sort of fundamental tensions of coroutines, is that you need to be able to sort of deal with this divergent, not really stack behavior. And it's worse than that. So for example, a lot of generator features, the generator, while it's in flight, is a first-class value that you want to be able to store to an arbitrary place in memory and then sort of iterate it as you go. That's something that is even further detached from the basic concept of a call stack, because the internal state of the generator while it's in flight can't just be stored on the ordinary stack. So how do we actually go about implementing that? Well, there's a lot of different considerations. The first one is about ceding control. So here's our generator function. You can see in here that we've got a couple different yield points. We have to do something when we're generating the code for this generator function that actually yields control at this point. There's a couple different basic implementation strategies here. The first one is context switching. So the idea is essentially like cooperative multitasking. You generate the coroutine like an ordinary function, except that at the yield points, you basically emit context switching code. You store the yield value in some place where it's going to be found by the caller, and then you call some runtime function. The advantage of this is that it's extremely simple for your compiler. It's almost entirely a runtime play. The disadvantage is that it ties up a stack, and that has a lot of overhead that you may not really be willing to embrace for your generator feature or whatever else you're doing. The other basic approach is called coroutine splitting. It's where you take that original function and you split it up into different functions. One function in particular is important. It's called the ramp function. It's the function that you enter in. It's the one that takes the original parameters of the coroutine. Everything else is a resumption function of some sort. And there's basically two families of approaches on coroutine splitting, although there's a lot of variation here as well. The first basic approach is a shared resumption function. So here is a coroutine with like a billion different yield points. Here is the ramp function. You enter it. It sets up the frame. It sets up the resumption function. That resumption function has to look like this. So you remember where you were as you're going along in the coroutine. You store that implicitly in the implementation. And then in your resumption function, the first thing you have to do is switch out again. So you're basically doing a double dispatch every single time you resume, if you actually have more than one yield site in your original coroutine. The alternative to this is per yield resumption functions. So again, we've got the special ramp function that takes the original parameters. But then instead of having a single resumption function, we've got one for each yield site, which means that when we resume exactly where we were. The advantage of that is it avoids that double dispatch if you actually were going to do it because you had multiple yields. But it's got some disadvantages about code size and some other complexities. So yeah. The second general kind of implementation consideration is how do we store the local state of the coroutine? We've got local variables and all sorts of other things. We need to store that somewhere. Well, there's basically three different things I'm going to talk about in this talk, three different approaches for this. The first one is a stackful coroutine. So the idea is that when we are invoking the coroutine for the first time, we actually give it a new call stack. Which we then have to actually deallocate when we exit the coroutine. Then every time you do a yield and resume, you're just context switching. So in terms of call stacks, that looks kind of like this. The tokenized sort of holds a reference to this other call stack on the side. When we go back and forth, we're just context switching. So this has some nice advantages. Again, it's very simple. It efficiently supports some really complex coroutine-like features, some of the things that you can do in Simula. It keeps everything off of the normal stack. That's all great. The disadvantages is that you get all of the normal disadvantages of having a call stack. Typically a coroutine is going to be a very small function. It's often entirely self-contained, or if it's calling things, they don't really participate in the yield, and you just come back to the original coroutine, which does the yield. So in fact, you only need a very small amount of stack memory for the coroutine itself, but you probably are required to allocate an entire page from your OS requirements. You've got a lot of wasted memory. Even if you can shrink it down, you're risking overflow because you basically need that call stack to be the maximum of the call stack depth at anything that you're going to do from your original coroutine. And it's got a lot of poor interoperation with other features, like the OS may not be happy that you're introducing your own call stack. Debuggers and other things like that probably need to know about the fact that you're doing this crazy stuff with call stacks, and so on. The second approach for local state is site allocation. So if we're splitting the coroutine function anyway, we've got to, when we enter the coroutine, each of these sub-functions that we split out, if there's any state that doesn't persist across a yield site, of course, that can just be ordinary local state of that sub-function. But if something does need to persist across a yield site, then that needs to be persisted somewhere. And where do we put that? We put that in an allocation that we make specifically for that case to handle that. So that looks, from call stacks, that looks kind of like this. The tokenized thing holds this abstract reference to a coroutine that is just, basically malloc to be exactly the right size for the local state of the coroutine. So that's great. It uses a very minimal amount of memory. It's not tied to a stack, but it does require heap allocation. And in fact, any sort of otherwise local allocation that you want to do in there also needs to be heap allocated. So typically, you are running into a lot of heap allocations, and you get all the disadvantages of heap allocation. For example, that you don't really get to guarantee success if you are in an implementation that really needs to care about system level concerns like allocation failure. Whereas if you were allocating that on a stack, it would be both faster and presumably something that you're willing to guarantee the success of. The third approach is what I call stack cohabitation. So here we push the frame, when we enter the coroutine, we push the frame in the normal way. When we yield, we return control to the outer function, but we don't actually pop anything off of the stack. So that looks kind of like this. So, tokenized calls words yields back. The words call frame is still sitting there on the stack. When tokenized calls put s, it actually goes on top of the coroutine frame for words. So this has some great advantages. It's guaranteed to use stack. It's a lot more flexible about what you do with the coroutine function. The disadvantage is that it's a lot more complicated for the code generator, and if your nesting of your coroutines isn't totally stacked, like if you need to do other allocations, if you've got multiple coroutines in flight at once, you can end up in a situation where you've kind of pinned things into memory and kind of fragmenting your stack in a way. The third class of implementation consideration is just, well, if we've got a generator, it needs to yield something back. How do we actually generate that? And there's really basically two different approaches here. So you can return something from your ramp and resume function, or just in registers or any other typical way that you would return a value. This is great if it's likely to be immediately used, as a generator probably is going to be. Or you can store it into memory somewhere instead of some fixed location, maybe in your coroutine frame. And this is good if it's going to be used much later, like in AsyncAwait, where you've got some sort of callback that's likely to be called on maybe a completely separate thread. So that ties me into the next concern. Well, I've talked about all these different considerations. How do we decide how we want to actually implement the particular language feature that we care about? Generators, the feature I ran through before on top of coroutines, these are typically created and run by a single caller, basically like a for loop. Often generator features are tied into for loop syntax, like I did in the example. That means that yield and resume is going to be relatively rapid fire. You want this to be a low overhead event. It's okay to sort of optimize the entire thing around that in a particular way. On the other end of the spectrum, we have things like AsyncAwait. AsyncAwait is really, it's not actually semantically wanting to do something like a coroutine where you've got two different functions yielding back and forth to each other and cooperating. Instead, AsyncAwait is actually basically using the coroutine mechanism in order to achieve a separate goal, which is that you have some function that needs to be broken up into a bunch of different callbacks that are going to be sort of threaded along as computation moves from function to from thread to thread as different things finish up. So basically, you are using the coroutine mechanism here for AsyncAwait as a mechanism for splitting the function up into all these different coroutines and persisting state across them. The implications of that are very different for how you want to implement your coroutine. So if I've got a read file function and a print, I forgot. Sorry, screwed that up. So yeah, the trade-offs that you want for AsyncAwait are very, very different from what you want for something like a generator feature. So I want to talk about here, in the context of those two things, I want to talk about what C++ does. C++ has a coroutine feature, the proposed one, but there's not really any sort of tagging to it. You actually don't know at an implementation level what the coroutine, how the coroutine is actually being used. It's just a language primitive that gives you this facility for breaking up the function into different pieces. And so the design pressure on it is a lot like the design pressure on lambdas, where you end up with this very abstract thing that hopefully the optimizer is going to magically eliminate all of the costs of. So the pressure there is to end up using something like async, and something that's really appropriate for async, and then hoping that the allocation and things like that will be eliminated statically in the cases that you really care about for something like a generator. And so that leads me to LLVM Coro. So what Gore implemented, which was intended for this C++ feature, and it very much shows that. I call this the switch lowering. I'll explain why in a second. It's really designed around the need of the C++ feature. So in the switch lowering, we have a ramp function that heap allocates a local state that always looks basically like this. This is a header with a resumption function. So the resume function, and there's a current yield state in here. You can see that this is leading towards that shared resumption function lowering that I talked about before. The result value, the value that's yielded back, is written into a static place in the coroutine frame. There's a lot of other characteristics of this that are very C++-y. It's set up to so that the ramp function is essentially a constructor. There's a separate destructor for that. That's sort of stored in the coroutine frame. There's a lot of care to support C++ things like exceptions. There's a lot of machinery in the lowering that's there specifically to support LLVM level optimization of coroutines and so on. There's things that really aren't used in C++, like Alloca, that aren't really supported in this, and so on and so forth. That's not a slur on Gore in any way. It's just, it is designed around the needs of the C++ feature. So in Swift, we had a lot of different trade-offs that we wanted. What we wanted is something that's really more of a special case of generators, so that we really need this very rapid back and forth. In fact, we expect most of our coroutines to be very trivial wrappers around basically, a little bit of pointer arithmetic and then using an address directly. So it's very, very important that this be minimal overhead, basically call level overhead. But it does need to interoperate with future language directions like async and await features that we're hoping to add in the future. I call this the returned continuation lowering in contrast to the switch lowering that's already there. So here's what we do in terms of all those different implementation considerations. We allocate into a caller-provided buffer. If that buffer is too small, then we have to heap allocate. That buffer has to be provided to both the ramp function and all the resume functions. The resume functions are spit out per yield. Again, that's so that you get a very nice little threading, and you don't have to do any sort of extra dispatch when you come back in. Because Swift uses its own calling convention, it was very important to us that we support a lot of things like being able to fully define the signature of that, maybe use our own special attributes, use our own special calling conventions. All of that is very flexible for us. But on the other hand, we don't support things like C++ exceptions in it, because that's not important for Swift. And we haven't put the same effort into it for supporting LLVM level inlining, because again, Swift expects that sort of optimization to be done by the Swift SIL optimizer, which is going to enable a lot of higher level optimizations. There's not really any point in optimizing something further at the LLVM level where you're going to, if you had the opportunity to optimize it at the LLVM level, it would have been better to optimize it at the SIL level instead, where you're going to get much better performance characteristics out of the resultant code. When I say that this is a new lowering, I'm not trying to imply that it's actually a completely different feature. I'd say probably 80–90% of the code is shared between these two lowerings. It's just some very low specific details about that need to be tweaked. So the things that are shared are things about some representation problems about splitting, about the local allocation and saving and restoring state at yield points. In summary, I hope that I've been able to convince you that coroutines are both a really interesting feature and a feature that really needs a lot of different flexibility, a lot of different variation for what your language in particular needs from the feature and what you need from the ABI of it. LLVM can't really reasonably just provide a single lowering for this. This is something that we need to support a lot of experimentation for and a lot of different possibilities. So thank you very much. Any questions?
All right. If you have a question, you can either use this mic or the mic in the center there.
Thank you, John, for the great talk. I'm wondering if you implement coroutine support at the seal level, you probably get more of the source language context and what you call the semantic intent. I wonder what the trade-off there is.
Yeah, so SIL has to be, okay, so coroutines are implemented at the SIL level in the sense that they are represented as coroutines at the SIL level. We preserve it all the way down into LLVM because it's just, one, because Coro existed and already does a lot of the liveness considerations, but also because we do actually care about LLVM optimization to a more limited extent. We do care about inlining things into LLVM and so on. And also LLVM actually does a quite good job at managing that kind of, simple liveness, sort of computation. Like there isn't much that we lose from doing the splitting and maintenance at the LLVM level from what we could do at the SIL level. We don't, like, the abstraction level of LLVM is appropriate for doing the splitting there. So I'm pretty happy with the fact that we do the splitting in LLVM IR.
Thanks, John. That was a really great talk. I just wrote down my question. You kind of touched on this in your last slide, but I was hoping you could expand on it. You mentioned the LLVM Coro intrinsics are very much tied to the C++ Coroutines TS, and that's one reason why you implemented your own coroutine mechanism for Swift. I understand the C++ Coroutines TS is not officially adopted in the working draft, so maybe that's part of the reason why you didn't decide to do this, but I was wondering if you think it's possible to adapt that to support both your use case and C++'s, and or are the two completely incompatible?
I don't think they're completely incompatible. I think some things about the structure, so a lot of the intrinsics are reused, right? So LLVM, Coro, and apply are basically the same. We needed slightly different things from suspend. I suspect that we could probably unify those. It's mostly the ID intrinsic, where you some of the structural rules around that really need to be pretty different based on the ABI. And I don't think that's really unifiable, but I think that's okay. It's just that, like, that's the point of divergence between the different coroutine structures. So I think everything else really preferably could be unified. I think there are definitely things that I did that probably ought to be adapted back into the main, into the, that could be used for, the existing coroutine intrinsics. I just didn't want to do that out of tree. I'm hoping to upstream all of this relatively soon. I wanted to make sure, sort of qualify these things, which is why I've been doing it all out of tree for a long time. But yeah, so there are definitely things that I think we could probably, things that we do that I did for the switch, for the Swift lowering that I think are the right way to do it and should be adopted by the switch lowering as well.
May I ask a follow-up question? Yeah. So you mentioned that you're developing this out of tree. Is that for LLVM, or is the Swift portion of this something that we could see in the open source repository?
Oh yeah. This has been open source for in the Swift fork of LLVM for about a year or so. Cool. It's just that we haven't put it in LLVM yet.
Awesome, thanks.
Yeah.
Hello. My question is whether can we use coroutines to lower green threads? If I use coroutines, would I be able to use one of these two backends, or would I have to invent something else?
So green threads are usually okay. So yeah, green threads are usually built on top of something closer. I talked about it here, but like. Yeah, you don't necessarily need this infrastructure to implement green threads, because typically green threads are built on top of basically a runtime technology. So, you just have your something behind the scenes, something that you call semi-regularly from your function, or something like that, swaps stacks for you. Like typically you don't actually do the compiler invasive stuff. And if you aren't doing the compiler, and if you aren't doing function splitting and things like that, then you don't really need the stuff that LLVM Coro gives you, because you are just doing stuff that LLVM just does normally. You're occupying a call stack, right? If you wanted to do a green threadish implementation that actually fundamentally changed the compilation model of normal functions, I think probably it just, LLVM isn't really built for that. Like, you don't necessarily want to turn every single function into a coroutine. You want, every single function to be compiled differently in a way that supports your green thread context switching model more efficiently or something like that. And that's a very, a very different model from what LLVM Coro provides, if that makes any sense.
All right, thank you, everyone. Thank you, John.